Hi there. Let's look at our last topic in geology, and that is understanding how fossils might create fossil fuels. Before we do that, though, let's do a couple practice problems. Last lesson, we talked about the geological time scale. We talked about how there's relative dating, which is not as exact, and there's absolute dating, which is an exact method of getting the age of rocks or fossils. So radioactive half-life is one strategy that geologists use to find the exact date of something. And so let's look at this practice problem that we'll do together. Someone wants to tell you a fossil is supposed to be millions of years old and therefore very valuable. You take a sample to check the radiocarbon date. The lab results say that there's about 93% of the daughter material, which is nitrogen, left in the fossil. So carbon-14 has a half-life of 5,730 years. How old do you think this fossil is? Is the owner telling you the truth, etc.? So let's go to full screen. In radioactive dating, we always start out with the parent material, and time 0, we have 100% of it. So it's all parent. After one radioactive half-life, what will happen is we will get 50% of the parent now, and now we have 50% of the daughter material. In this case, we have carbon-14 was the parent material, and it turns into nitrogen. That's the daughter. So that's one half-life, which in this case is 5,730 years. After two half-lives, we now divide this again by 2, so we have only 25% of the carbon-14, and we now have 75% of the daughter material. So this is the nitrogen, and this is the carbon. We need to get to 93% of the nitrogen, which is the daughter. So that's two half-lives, which again is another 5,730 years. So let's keep going because we need to get to 93%. We're only at 75. So we divide this by 2 again, so it goes down to 12.5. So after 3 half-lives, we have 12.5 of the carbon, and the rest is made up of the nitrogen, which is now 87.5. So that's another 5,730 years. We're still not there. We need to get to 93, so let's divide 12.5 in half again. So that's 6.75. And this will be 93 approximately, if you round. So that's 4 half-lives. So it took 4 radioactive half-lives, so that's another 5,730 years have gone by. So 1, 2, 3, 4 rounds of 5,730 years. Let's use our calculator. 4 times 5,730
equals 22,920.
That's how old your rock sample is. Is it millions of years old? Nope. Is the owner of it telling you the truth? So should you buy the sample? Absolutely not. It's not old enough to be valuable at all. Let's talk about fossil fuels today. How do we make fossil fuels? Well, fossil fuels come from dead, decaying organisms. And there are three types: coal, oil, and natural gas. Most oil is formed where there was marine environments. So let's look at my picture. Trees, plants, and animals absorb sun's energy. The sun's the ultimate energy source. The remains of these trees, plants, and animals go into the ground and decay, and the earth crushes the fossils and converts this into what we call fossil fuels. Oil can almost be considered a liquid version of coal. Oil is often found underground in dome-shaped places directly above coal deposits. Natural gas is thought to have been created from large amounts of plant material that did not become coal. So here it is again. How do fossil fuels form? We have years and years and millions of years ago, there was lots more sea, material washed up from the sea. Living material dies, remains of plankton, which are kind of tiny sea life, layers of sediment build up. Parts of the dead materials are changed into what we call hydrocarbons. Layers build up even more and they compress, and then gas, oil, and water can get trapped into these layers. Sediments form, so you get a gas deposit, an oil deposit, and so on in the layers of sedimentary rock. How do we know it's there? So in other words, this is deep into the crust. Not too deep. Don't forget we talked about long ago that really the deepest we've ever drilled into the crust is 12 kilometers. So we use something called seismic waves, which we talked about before with earthquakes. So on land or in the sea, we can send out certain types of sound waves which will bounce back to a hydrophone or a receiver, and this receiver detects how quickly it came back the um, to the receiver, and a computer can tell based on the fact that oil and water have different densities whether there's oil underground in the crust in different sedimentary rocks. We can drill for oil once that happens. So once we know that there's oil and then maybe a gas pocket above, then we can drill for it. We also have a new technique called horizontal drilling. So let's say there's a lake over top of where your oil deposit is. New technique, you can drill down and then horizontally so that you don't disturb the ecosystem above like this. We can also drill offshore. So there's all sorts of different offshore platforms that are used. So kind of some neat anchoring techniques here. Just to put things in perspective, here's sort of a graph showing you the amount of crude oil around the world based on countries. And so Saudi Arabia, Kuwait, Iran, Iraq, Russia, and so on. There are different types of oil which are deposited. The trickiest type is something called bitumen. Bitumen is a really sticky tar-like substance, and it must be heated or diluted into water in order to get at it. And our oil sands up in northern Alberta and Athabasca mostly is bitumen, which it's trapped in the sand there, and it's hard and expensive to extract. If we're lucky, oil will come in a different format, which is light crude oil. It's more liquidy, it's got a lower density, and it flows a lot freely. Because it's got a low viscosity, it can be extracted a lot easier. So we can use these pump jacks, or horses if you will, to get at oil that's not bitumen, because we can simply flush water in and it'll come up this way. So steam comes in, it kind of flushes the oil up through a piping system. However, in the Alberta oil sands, which is located sort of in this part of Alberta, the oil extraction process is a little more complicated. The oil sand is mined and then loaded into trucks. The truck delivers the sand into crushers where it's broken down and then stored, and then screened hot water is added to crush the ore and transform the dry oil sand into kind of a slurry mix. And then based on the different weights and densities, oil sand and water mixture is transported to a separator. So the bitumen is then screened off. Bitumen froth is treated with a special liquid or solvent, and then the final product is piped for upgrading to various petroleums. And then this is where the controversy comes. Tailings and sand are dumped into what's called tailings ponds, and these are usually outdoor. And the latest controversy in the news has to do with the fact that ducks and other wildlife are landing on these tailings ponds, which can contain still bits and pieces of the bitumen in there. Let's look at the video clip on fossil fuels.
Dear Tim and Moby, my teacher said we're running out of fossil fuels. Does she mean gas? From Maddie. Hey Maddie. Natural gas, along with coal and oil, are all known as fossil fuels. We use fossil fuels to heat our homes, run our cars, and power industrial plants. And more importantly, we're using them now to cook these hot dogs. Oil and natural gas are similar because they're both types of petroleum. Oil is the liquid form, natural gas is the gaseous form. Petroleum is the transformed remains of tiny marine plants and animals from millions of years ago. That's right, Moby, dead plants and animals. Yeah, well, enjoy your hot dog. Anyway, when these animals died, their decaying bodies sank to the bottom of the ocean or swamp they were living in. Eventually, they were covered with layers of sand and then stone. Time and pressure went to work on them until they became pockets of petroleum in the earth. Petroleum is found in underground wells, both on land and offshore. Miners use big drills and pumps to get deep into the earth's crust and find petroleum. Oil and natural gas are really valuable. Natural gas is mostly made of methane, and it's usually found near oil deposits because they're created under similar conditions. The gasoline that cars run off of is made from refined oil. If you have a gas stove, then you've seen natural gas in action. Both oil and gas can be burned in power plants to generate electricity. Another type of fossil fuel is coal. Coal may look like a rock, but like the other fossil fuels, it too was once living matter. Prehistoric plants died and sank into the swamps and bogs. Over time, they were covered with layers of rock and earth, creating enough pressure to slowly squeeze them into a solid. Coal is extracted from the earth by digging large and complex mines. Coal was used heavily as a fuel source during the Industrial Revolution and is still commonly used today. So fossil fuels are good energy sources. Just one tank of gasoline can take a car hundreds of miles. They're also pretty convenient because they don't need too much processing. Unfortunately, burning fossil fuels creates a lot of pollution. You know this if you've seen coal-burning smokestacks or opened the car window while stopped in traffic. Carbon dioxide, which contributes to global warming, is also a byproduct of burning these fuels. Right now, oil, gasoline, and natural gases account for about 60% of the energy used in the world, and it might be hard for people to change. Problem is, we're using fossil fuels much faster than the Earth can produce them. Fossil fuels are a non-renewable resource. That means they can't be replaced after they're gone. At our current rate of consumption, we will probably not have enough oil and gas to last us through the next century. Luckily, there are alternatives to fossil fuels. Lots of research is being done on developing solar power, a clean, cheap way to harness the awesome power of the sun, and nuclear power, a way to harness atomic energy. We still use other, older ways of harnessing energy like water and wind.